topic where we are familiar with these type of elementary discrete time signals which are frequently used, but we will look at their discrete time representations. So first, the signals are unit impulse, unit step, unit ramp, and exponential. And as we know, there are two types of exponential signals: real exponential and complex exponential. So let's quickly go through the signals. So a unit impulse signal, so the unit means the amplitude is 1, and the impulse, as we are aware from the continuous time or signals, it is a signal with an amplitude occurring only at origin, and elsewhere it is not existent. Similarly, in the discrete time domain, unit impulse is represented by small delta n, and is defined as a signal which has a value of 1 for n equals to 0, and for all other values of n it is 0. So when we can either write in this format: delta n equals to 1 for n equals to 0, and 0 for n not equals to 0 or otherwise, or we can write as delta n is equal to, in a sequence form we use the curly brackets and we write 1, and within underneath 1 there is a vertical arrow indicating that this is the origin, and this means that on the left and on the right hand side there are the values of the signal are 0. To further elaborate this representation type, we can also write the same signal as in this format. So you now know that when we say the signal is delta n, it means we are talking about a unit impulse signal, and where the value of 1 is at n equals to 0, and for all other values of n the signal has 0 values. Remember that in case this value is not 1, it is 2 or 3 or -1, then still it will be an impulse signal, but not a unit impulse signal. The amplitude of the signal is 1, then we call it a unit impulse signal, and this is used quite often in signal and system analysis, and you will see this signal, this symbol representing a lot of time, repeating a lot of time during our course. This is the graphical representation of a unit impulse signal. You can see that all values are 0, and at n equals to 0 we have a signal whose amplitude is 1, and it is represented by delta n. Now let's look at the second signal type, which is a step signal, and here we are looking at a unit step signal. A unit step signal is represented as u of n, and is defined as un is equal to 1 for n equals to n greater than or equals to 0. So for n equals to 1, n equals to 0, and all positive values of n, the signal has got an amplitude of 1, and for negative values of n, for n less than 0, it is 0. So this is a unit step signal, and the word unit comes to represent that the step from 0 to 1 is of 1. And again, as I indicated earlier, that this can happen, that you may have a step signal like 0 0 0, 2 2 2 2 2, and so on. So in that case it will still be a step signal, but not the unit step signal. And the relationship between the impulse signal and the step signal is that if we make the summation or the integration on the impulse signal, we get the step signal, and when we differentiate the step signal, then we get the impulse signal. Graphically, a unit step signal looks like this. It has 0 values for all negative values of n, and for n 0 and positive, we have the amplitude as 1. Okay, let's look at the third signal type, which is unit ramp. As the word ramp indicates, The unit ramp signal has the values increasing with increasing value of n. So it is represented by u subscript r of n, and it is defined as u of r of n is equal to n. The values will be n for n greater than equals to 0, and for all negative values of n, urn will be 0. So as you can see in the sequence representation, for all negative values of n it is 0, and when n is 0, the value of the signal is 0. When n is 1, the value of signal is 1. When n is 2, the value of signal is 2, 3, 4, and so on. So this is a unit ramp, and the word unit is there because the gradient which is formed from these values is 1. So 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1. So the slope which is forming out of this ramp signal is that of 1. That's why it is called a unit ramp signal. And as you can quickly note, that if we integrate a unit step signal, we get a unit ramp signal. And similarly, if we differentiate a ramp signal, then uh, we get a step signal. So the impulse signal and the step signal and the ramp signal, they are related through the relationship of integration and differentiation. Graphically, the unit ramp is represented like this. So all values are 0 for n less than 0, and from n 0 and onwards, you've got a slope of 1, and the values are 0, 1, 2, 3, 4, 5, and so on. Right, so let's move on to exponential signal. So to make life simple, um, let us first note that any exponential signal in discrete time, whether real or complex, is represented by this form. X of n will be equal to a raised to power n for all values of n. Okay. Now, as soon as you see this type 0.3 raised to power n, or 1 upon 4 raised to power n, or minus 1 raised to power n, so you got to know that this is an exponential signal. Now the question comes that whether this is a real exponential signal or a complex exponential signal. So the answer is also very simple. You forget n, you look at a. If a happens to be a real number, like just I give the example 0.4, 1 over 4, 0.1, minus 2, whatever. If a is a real value, then this signal will be a real signal. If a happens to be a complex number, then your exponential signal will be a complex exponential signal. But regardless of whether it's a real exponential or a complex exponential, the form of an exponential signal, discrete time exponential signal, will be a raised to power n. And if a is real, as I indicated, then xn will be a real signal. Okay, so for now what we are going to do is to look at some real exponential signal examples and try to make some observations out of it. So what we are going to do is this. Okay, we take a signal xn is equal to a raised to power n, and we say, okay, for various values of a, we will calculate the value of xn. And for our simplicity, we define that, okay, the values of n will be 0, 1, 2, 3, 4, 5, and 6. So for these values of n, we will try to figure out the signal values of a raised to power n. So here in this table, you can see that the first row is that of n. So n is 0, 1, 2, 3, 4, 5, and 6. Okay, and these different rows are the signal values for various values of a. Okay, now let us take one example at a time. I choose a equals to 0.9. So my signal is going to be xn is equal to 0.9 raised to power n. So if I want to calculate the values of this, Then for various values of n, it will be 0.9 raised to power 0, 0.9 raised to power 1, 0.9 raised to power 2, 0.9 raised to power 3, 0.9 raised to power 4, and so on. So this table, this row, the second row, indicates all the signal values when the value of a is 0.9, and it is calculated for all these values of n. So now observe that for 0.9 raised to power 0 is 1, 0.9 raised to power 1 is 0.9, 0.9 raised to power 2 is 0.81, 0.73, 0.66, 0.59, 0.53. So now you see that as the value of n is increasing, the value of the signal is decreasing. So it starts with 1, decreases to 0.9, 0.81, 0.73, 0.66, 0.59, 0.53. So this is going to end, and this is going to converge uh, towards 0. Then what I do is I take another value of a. Now this is 1. So the signal values will be 1 raised to power 0, 1 raised to power 1, 1 raised to power 2, 1 raised to power 3, and so on. So for all, because it is 1 raised to power whatever, then all the values will be 1. So now we see that the signal values are not decreasing, they are just remaining constant like a DC signal. Okay, so in this case it was decreasing, in this case it is constant, and if I increase this value beyond 1, I take it as 1.10, then you can note that the value of 1.1 raised to power 0 is 1, then raised to power 2 raised to power 1 is 1.1, 1.21, 1.33. So here we are getting a signal which is expanding, and it is not converging, it's just diverging. And if we continue to increase the values of n, this will quickly go towards infinity. So here it is a converging stabilized signal, here it is a constant signal, not dying out, not expanding, not diverging, and here it is a diverging signal. If we continue to increase the value of n, then this can go towards infinity or instability pretty quickly. Similarly, there are these three examples are again the same values but with a negative sign. So minus 0.9, minus 1, minus 1.1. So what's happening is that with minus 0.9, again the signal values are decreasing, but there is an oscillation. So first value is positive, the other is negative, then positive, then negative. So you get the signal values on both sides of the x-axis. So positive y-axis, negative y-axis, positive y-axis, negative y-axis, positive y-axis, negative y-axis, and so on. But still it's a converging signal, except that the oscillations are there for all these three types. Here it's 1, minus 1, 1, minus 1, and so on. And here it is 1, minus 1.1, 1.21, minus 1.3. It's diverging. So what we see here from this example is that as long as the value of A, the magnitude of A is between magnitude of A is less than 1, uh, we will be generating a converging exponential signal, whether in the positive direction or in the negative direction. But as soon as the magnitude of A go beyond 1, we start to see the exponential diverging signals. Now this thing is more clear when we look at the graphical format. So it says that if the real exponential signals have the value of A between 0 and 1, then you get a converging signal type. If the value of A goes greater than 1, it increases, it starts increasing. This is a sign of instability. If the magnitude of A is still less than 1, but the sign is negative, so it is between 0 and minus 1, we will still get a converging signal. However, there will be an oscillation. The signal will be on both sides of the x-axis. And lastly, if the value of A is less than minus 1, then again we will get a divergent signal, which is the sign of instability, and this time it will be on both sides of the x-axis. Right, so now let's look at the complex exponential signal. As I mentioned earlier, that the form of the exponential sequence will remain same, a raised to power n, but a will now become complex, and as soon as a is become complex, then the exponential signal becomes complex. So for example, I now take the value of a as not a real number but a complex number representing in a phasor format r e raised to power j omega d. Then a raised to power n will become, so instead of, in place of a, I can write r e raised to power j omega d raised to power n. So if I expand this, this becomes r raised to power n into e raised to power j omega dn. And if I want to expand omega d, I can write it as 2 pi fdn. So this will be r raised to power n into e raised to power j 2 pi fdn. We know that from Euler theorem, e raised to power j theta can be expanded into cos theta plus j sine theta. Using that expansion, xn can be written as r raised to power n into cosine of omega dn plus j sine omega dn. Now, here the important thing to remember is that there are two components. One is r raised to power n. Now, this r raised to power n is very similar to the real exponential we have already seen, where we have seen the value of a to be either between 0 and 1 or greater than 1 or between 0 and -1 or less than -1. So in that case we get different type of envelopes. So this r raised to power n is exactly the same thing. The value of r will define that what will be the envelope shape of this exponential signal. Regardless of the oscillations coming from cosine and sine, this r raised to power n decides whether these oscillations coming from cosine or sine will die out or will remain same or will just go unstable and will expand. So that depends on the value of r. If it is less than 1, then whatever the oscillations coming from cosine and sine, they will be multiplied by r raised to power n and eventually die or will remain same or will go up. So in exponential signals, one of the things to look for is the value of this r, which is the real number. If it is less than 1, we will have a if the magnitude is less than 1, we will have a stable signal, and if it is beyond 1, then it will not be a stable signal. And how fast or slow the oscillations of that exponential signal will be depends on omega d, depends on the frequency omega d or fd. If it is high number, then there will be more oscillations. If this is a low number, there will be less number of oscillations, just like in any other cosine or sine wave. So I know you know these things, but for reference I have repeated this here, that this r raised to power n cos omega dn plus j sine omega dn, or in terms of fd, this can be represented in either in real and imaginary format, where the real signal is r raised to power n cos omega dn and the imaginary signal is r raised to power n sine omega dn. Or you can represent the complex exponential in the form of magnitude and phase. Rather than the Cartesian format, we can go to a polar format where we would like to see the magnitude and the phase. So in that case, if we take the mod of this expression, mod of xn, we end up as r raised to power n, because cos square theta plus sine square theta will you get 1 and you are left with r raised to power n. So this is the magnitude. So this will be very similar to the real exponential, and the phase will be represented by the argument of sine and cos, which is omega dn or 2 pi f dn. So for an example where we take r equals to 0.9 and fd equals to 1 over 20 cycles per sample, omega d will be equals to 2 pi, 1 over 20 is pi over 10 radians per sample. So remember r is 0.9, so this has got to be a stable signal, and the oscillations will be depending on pi over 10. So the real and imaginary representations as well as magnitude and phase representations will be looking like this. So this is the real and imaginary part. You can see that the curve is coming down. If we just forget about this oscillations for a little bit and draw the envelope, then we see that this is coming down and stabilizing towards zero. This is happening because of this 0.9. Had this been 1.1, then these oscillations will be increasing with the increasing time. And this is a cosine. As you can see, it's starting from 1, so this is a cosine component, and this is starting from 0, so this is a sine component. So this is a real and this is the imaginary part. And the same signal, if you look at its magnitude and the phase response, then you can see that the magnitude signal shows that this is a stable signal, while the phase omega d n with the increasing value of n oscillates between minus 2 pi and plus 2 pi. So this is regarding the discrete time representations and some elementary signals. Now let us move towards